Then let's look at some common functions in physics. Let's start with a linear one, which takes the form y equals mx plus c. And if I plot that as a graph, it's a straight line. And if m is the gradient, which if that's negative, then the graph is going to look like this with a negative gradient. And if the y-intercept is negative, then that's going to go below the axis with a negative intercept, like in the y-axis. Okay, common examples of this during the photoelectric effect, the maximum kinetic energy of the electron against the frequency, or the terminal voltage across a circuit against the current, like so. It's easier to see if you write like this. It takes the form y equals mx plus c. An important subset of linear functions is directly proportional, and that's called the equation y equals mx. So it basically doesn't have the plus c because it goes through the origin like so. And this is important because it has additional features, like if y doubled, then x would also double provided the gradient there is constant. Examples include Ohm's law, which is potential difference is directly proportional to current if the resistance is a constant. Resultant force against acceleration if m is a constant, and the energy of a photon against frequency. Another important function in physics is the quadratic one, also known as parabolic, and that has the form y equals kx squared, where k is a constant and it's going to curve upwards like so. Examples of this is displacements against time for something that's undergoing constant acceleration, power across a component where resistance is a constant that's proportional to v squared. Okay, and then elastic potential energy stored in a spring that's stretched as long as it's following Hooke's law and k is a constant, it's directly proportional to the extension squared. Okay, we can continue raising x to higher powers, not just squared, but cubed and so on. And that has this form where n is a number that is bigger than 1, and it's just going to curve more like this. Okay, next one is the square root function, where we can write that as y equals k times x to the power of half, or even better, you can just write it under a square root like this. And the graph will look a bit like this, okay, with the gradient decreasing but not reaching 0. So it doesn't flatten out, it's just a constantly decreasing gradient. Okay, examples of this function include the velocity of a charged particle is when it's accelerated through some potential difference. If the charge is constant and the mass is constant, it looks a bit like this. Or the frequency of a stationary wave on a string, where t here is the tension along the string. Another important one is inversely proportional, which can be written as y equals some constant over the x there. Okay, and the graph looks like this. And the important feature of this graph is that it doesn't touch the x-axis and the y-axis. It's asymptotic at those 2 points there, so it doesn't touch those axes. Examples is current and resistance. So the higher the resistance, the lower the current, but it's a unique one. So if I double the resistance, I would halve the current. Okay, another example, the width of a fringe in a double slit pattern against slit separation, or the pressure of an ideal gas against volume. Next, we have the inverse square law, which is very similar to the inverse proportional one, except there's a squared at the bottom like so. So you got y is equal to some constant over x squared. The graph looks very similar to the inverse proportional one. It's asymptotic there and at the x-axis and the y-axis, so it doesn't touch those axes. Examples of this function include Newton's law of gravitation, where the force of gravity between two objects is inversely proportional to the distance between them squared. And this is unique because what it tells us that if you double the distance, the force becomes a quarter. Okay, if you triple the distance, it becomes a ninth. Same with intensity from a light bulb or some radioactive source. It's inversely proportional to the distance from the source squared. Okay, next common function is the sinusoidal ones. So for example, y equals some constant times sine x, and that takes a form like this in the graph. Okay, they can also have another common one, which is y equals a cosine x, where a is a constant again. Okay, and that's the same function, but it's just shifted towards the left by 90 degrees. Okay, examples of this, let's say the acceleration of a mass along a slope. So that's a equals g, which is 9.81 sine theta, where theta is this inclined slope. Or you can have the displacement of a object undergoing simple harmonic motion, where omega is a constant that's to do with the frequency of the oscillations. Or you can have this one here, which is for the EMF induced in a coil that's spinning. Okay, you can also square the trigonometric function. Okay, if you square it, then that means you won't have negative values. Okay, the negative values come to the top like so. Okay, so on the dotted line you've got the cosine function, but once you square it, you can see it's going to the top side, so you don't get any negative values. Example of this is during polarization, when you have two polaroids and you're spinning them, the intensity varies like so. When they're parallel, you get maximum intensity, and they're perpendicular, you get minimum. Next common function is exponential decay, which has the form y equals some constant e to the power of minus x there with the k as a constant, and looks very similar to the inverse proportional one, except this time this one touches the axes there. Okay, it doesn't touch the x-axis though, it's asymptotic here, but on the y-axis it does touch that. Okay, examples include the number of reactive isotopes against time that decreases exponentially, or the voltage across a capacitor as it discharges, it decreases exponentially as well with time. I'm not quite sure what the strict name of this function is, but I'm going to call it inverted exponential. And it has the form y equals a, which is a constant, then 1 minus e to the minus some constant times x. Okay, so it's basically similar to the function we had earlier on, but we have the 1 minus there. So it looks a bit like this. Okay, and then you've got an asymptote over there. Okay, so that's going to be asymptotic with a at that value there. Okay, so examples include when you're charging a capacitor and the voltage levels off at V0. Okay, or the charge on a capacitor also leveling off at Q0. The final function, which you only really come across once in physics, which is the elliptical or circular. Okay, so it has this form. It's got some x squared and y squared and then some constants there. And you can also rearrange it into this form, which is how you'd probably encounter it. So it looks the shape of a ellipse or a circle. And the key idea here is that it's got two solutions at any given x point. Okay, and that sometimes you have it written with a plus or minus at the front, because when you square root something, you can get positive or negative solution. This example here is for a velocity of an object that's oscillating back and forth undergoing symbolic motion.